Hi, my name is Lu Pan. I'm from Meta. Today I'll talk about cache invalidation and cache consistency, which are generally considered hard problems in computer science. And I will talk about how we manage the complexity at Meta at scale. My goal of the talk is to help reduce engineers' suffering from cache invalidations and help make all invalidation-based caches in the world a little bit more consistent along the way. There's a meta engineering blog post on the same topic, where you can find more details. The word cache was first introduced in 1967 as a better word for high-speed buffer. Cache helps scale a read-heavy system, reduce latency, and save cost. They're literally everywhere. Caches running on your phone, in your browser, CDN and DNS are essentially geo-replicated caches. Many caches are working behind the scenes, so you can watch this very presentation right now. I've been at Meta for more than 6 years, and I spend most of the time working on cache consistency on some of the largest cache deployments in the world. For example, TAO is the cache that provides primary access to the social graph, which serves more than 1 quadrillion queries a day. I care deeply about cache consistency because prolonged cache inconsistencies are indistinguishable from data loss from users' perspective. For example, say Alice accepts Bob's friendship request, and they're not friends. Notice that the cache is inconsistent with the database. A few days later, Alice asks if she and Bob are still friends. Getting a reply from the inconsistent cache, Alice would receive a negative answer. So from Alice's perspective, it's as if her earlier write were lost. Given that cache is ubiquitous and has been around for more than half a century, one might assume we must be very good at keeping caches consistent at this point. But there is this famous quote from Phil Carton saying, "There are only two hard things in computer science, cache invalidation and naming things." And we all know how hard it is to name things. So it at least suggests that keeping caches consistent using invalidations is not an easy problem. So what exactly is cache invalidation, and what is its relationship with cache consistency? By definition, a cache is not the source of truth. Cache invalidation describes the process of actively invalidating cache entries when the source of truth mutates. If a cache invalidation is mishandled, you will end up with inconsistent data in your cache indefinitely. In the example here, the database and its supporting service are sending the invalidations. While they don't have to come from the database, for example, clients can be responsible of invalidating cache entries as well. Caches that solely depend on TTL or time to live for maintaining freshness don't have invalidations. Hence, they're out of the scope of this talk. So why cache invalidation? This seemingly very straightforward process is one of the hard things in computer science. To answer this question, let's start with a very simple mental model. A cache, at its very core, is still a stateful service that stores data. If we zero in on a single addressable block where we store a piece of cache data, we want to know what's changing its state and if they're done correctly. Distributed systems are essentially state machines. If every state transition is correctly performed, we will have a distributed system that works as expected. Otherwise, we have a problem. So the key question here is what's changing the cache data state? So for example, for a static cache, the source data is immutable. Cache state only changes on the read path. A simplified version of CDN fits in this model. For databases, the state only gets mutated on the write path. Reading a database naively doesn't change its state, except for caching. Databases are hard to build. These are just the simplified mental models. I'm not trying to minimize anyone's struggles. For a dynamic cache like TAO and Memcache, the state gets mutated on both the read path for filling caches and the write path for cache invalidation. It is exactly this conjunction that introduces many race conditions that makes cache invalidation a hard problem. Data in cache is not durable, which means sometimes important version information for conflict resolution might be evicted from cache. And so far, we're still only talking about a single data block on a single cache host. In reality, we have distributed fault-tolerant cache on top of many dependencies where failure recoveries, failovers, shard movements, etc. are happening constantly. In combination, a dynamic cache produces so many race conditions that are just beyond my wildest imagination. Here's a quote from the end of Google's Paxos Made Live paper. It says, "It appears that the fault-tolerant distributed computing community has not developed the tools and know-how to close the gaps between theory and practice." Cache invalidation is hard, not only because of the complexity of cache invalidation protocols to keep cache coherent. Additional challenges are in measuring how consistent the cache service actually is, and answering the even harder question of why it is inconsistent. Designing a consistent cache is very different from implementing and operating a consistent cache. Just like designing Paxos, the protocol, is different from building Paxos that actually works in production. Over the years, we improved the TAO's cache consistency by one measure from 6 nines to more than 10 nines. We'll talk about how we did it in some future work in this talk. The approach we took should be generally applicable to most, if not all, cache services with invalidations. 6 nines might sound pretty good to start with, but it's not good enough at meta scale. So what can go wrong when cache is inconsistent? Take TAO for example. As meta grows over time, TAO stores not only data for rendering a page, for example comments and likes, but also control data. Generally speaking, control data has a stronger consistency requirement. There's a messaging use case at Meta that maintains a mapping between users and regions where the primary message stores are located. The map is stored in TAO. There's a reshuffling process that updates the map periodically. Every time you send a message to someone, behind the scenes, it queries TAO to find out where to route the message to, so it gets stored in the right place. Many years ago, when TAO was less consistent, after reshuffle, some TAO replicas will be inconsistent, leading to split brain for the messaging use case. Here, if Mary hit an inconsistent TAO replica, the message could be routed to the wrong region. Now, neither region has a complete copy of Alice's messages. The issue was brought to our attention, and I checked the cache. It was indeed inconsistent. Now, I'm not sure how you would react in such a situation, but this was when I experienced the 5 stages of grief, starting with denial. And my service and my code is just perfect. This is impossible. Blame the dependencies. But eventually, I had to accept the reality and then figure out how to fix it. First off, we don't want our users to tell us if our caches are consistent or not. We need to have reliable cache consistency observabilities ourselves. What do I mean by that? We want to measure the consistency and alarm when there are inconsistent entries in cache. The measurement can't have any false positives. Human brains are very good at filtering out noises. If the measurement has any noise, people will learn to ignore it very quickly. Second, we need the measurement to be precise, as we're talking about measuring up to more than 10 nines of consistency. If a consistency fix is landed, we want to be able to quantitatively measure its improvement. Knowing how consistent our caches are is great, but it's just not enough. Just like any good constructive feedback, it needs to be actionable, so we can actually make the system better. We built a service called Polaris that solves the measurement problem by focusing on client observable invariants. If an anomaly can't possibly be observed by a client, I argue it doesn't matter at all. A typical cache Polaris integration looks like this. It samples cache invalidation events and verifies if all cache replicas are consistent or not. It is deployed as a separate service, so it scales independently from the production service and its workload. With Polaris, we define consistency metric that looks like n nines of cache writes are consistent within n minutes. You can find more details about Polaris on the Meta Engineering blog post. At the beginning of the talk, I showed this number. It is measured by Polaris at a 5 minutes time scale. It means that out of 10 billion cache writes, less than 1 of them would be inconsistent in cache after 5 minutes. Now we have the measurement. We need to figure out why caches are inconsistent and how to fix it. For most part of this talk, I'm using one simple box to represent cache, but in reality, it looks more like this. The gist of it is that cache can fill itself from different upstreams, and the invalidation can come from different regions out of order. I have a challenge for you. In this simplified diagram, can you spot where cache inconsistencies can be introduced? It is a trick question because all of them can. Any problem from any component in the system in any scenario can potentially cause cache inconsistencies. And we have seen cache inconsistencies caused by databases, pub/sub, host management, shard movement, and of course bugs in the cache server itself. I'll give you an example at the end of this talk. Promotions, failovers, failure recoveries, network partitions, hardware failures, these things happen all the time. Things can potentially go wrong in a million different ways. So how can we even get started at debugging the inconsistencies? How can we find a tiny needle in a massive distributed haystack? Will Wilson from FoundationDB once said, debugging a distributed system is preferable to stick a fork in your eye. But not that preferable. It's actually surprisingly close. It is true. In my opinion, debugging an inconsistent cache makes them feel even closer. But why? What makes cache invalidation debugging particularly hard? Let's take a look at a real bug we found and fixed this year. I'll talk about the issue first, and then I will come back to what actually happened at the end of the talk. In one system, we version each piece of data for ordering and conflict resolution, and we observed this. The cache said metadata should be 0 at version 4, but the database said it's actually 1 at version 4. The cache stayed inconsistent indefinitely. It should have been impossible. Imagine you are the one who works on a cache service, and you have the most brilliant cache invalidation protocol implemented, and this happened. How would you debug this? Whatever you do, don't poke a fork in your eye. A common first step is to add more logs. Distributed systems are state machines. Assume one can log and trace every state change that affects, for example, leadership, shard ownership, failover, retries, and every cache data mutation. Then when an anomaly is detected, we will have all the information to help us debug. The deal breaker is that it's almost impractical to log and trace every cache state change. Cache state changes on both the cache fill pass and the cache invalidation pass. A cache is often introduced to scale a super read-heavy workload. It implies that most of the cache state changes are coming from the read pass. Taking TAO, for example, which serves more than 1 quadrillion queries a day, even if the cache hit rate is 99%, we'll be talking about doing 10 trillion cache fills a day. Logging and tracing 10 trillion mutations a day is very computationally expensive. We can't sample the logs either. Cache inconsistencies are so rare. Sampling the logs makes the log useless most of the time. Can we do something smarter? What if we only log cache mutations where and when cache inconsistencies can be introduced? Let's look at a simple race condition. The cache first sends a fill request to the database, and before the reply 42 reaches the cache, someone mutates the database value to 43. The cache invalidation event of the latter 43 reaches the cache first. Finally, when 42 from the earlier cache fill request reaches the cache, it changes the cache value to 42. Now we have 43 in the database and 42 in cache indefinitely. There are many ways to solve this simple problem. For example, we can add version to resolve conflict. But what if 43 is evicted from cache before 42 arrives? And the cache has no knowledge of a conflict to begin with. It's a fun problem, right? Now, this is only cache consistency problem on a single cache host. In reality, we're dealing with a complex distributed system producing endless possibility to create cache inconsistencies. Our goal here is to find a simple solution to help us manage this complexity. The idea is to look at the entire problem from a single cache service perspective. Because at the end of the day, an inconsistency has to be materialized on a cache host. So from its perspective, it only cares about a few things. Did it receive the cache invalidate? Did it process the invalidate correctly? Did the cache item become inconsistent after the invalidate? And nothing more. This is the same example but illustrated on a space-time diagram. First comes the read request from client. Client sends a fill request to the database. Before the cache receives the cache fill reply, client initiated a write to the database, which triggers a cache invalidation. Finally, the cache fill reply reaches the cache host. If we focus on the cache host's timeline at the bottom, we see that after a write, there's a window in which both the invalidation and the cache fill can race to update the cache. After a while, the cache will be in a quiescent state in which cache fills can still happen at a high volume, but it's less interesting from a consistency perspective because there are no writes. It essentially becomes a static cache. We only need to log and trace cache mutations in this small purple window, where and when cache invalidations can be mishandled and the cache inconsistencies can be introduced. The purple window also captures the conjunction between the racing write path and the read path, which we mentioned earlier. The insight here is that cache inconsistencies can only be introduced after a write, because to mishandle a cache invalidation, you need to have an invalidation to begin with. But more specifically, it can only be introduced in a short time window after a write, when racing cache mutations can take place. So all the interesting, complicated interactions between racing cache fills and invalidations happen in this small purple window. This is also when bugs get triggered that lead to cache inconsistencies. Now we can log and trace cache state changes in this purple window to help us debug. The absence of the log can also tell us if invalidation event never arrives. To do that, we built a stateful tracing library and then embedded it into a few major cache services at Meta. It logs client writes and trace invalidations. It also buffers an index of recently modified data for a few minutes, which is used to determine if subsequent cache state changes of the same entry should be traced or not. It supports code tracing as well, so we know the exact code path for every traced invalidation and a cache mutation. It can tell us all the interesting things we need to know to debug inconsistencies. Now let's come back to the inconsistency that we ran into earlier this year. Consistency tracing helped us solve the mystery. So this is what happened. There is a very rare operation that updates two tables in this database transactionally, the metadata table and the version table. The cache tried to fill the metadata with version. The fill operation was done in two separate read transactions. In this case, the cache first read the old metadata. Then this rare transaction came in and updated both the metadata and the version table atomically. In the second round, cache filled the new version data. Here, the cache fill operation interleaved with the database transaction. This type of torn read is very rare. I know what you are thinking. You are thinking this is the bug. But no, it's not. So far, everything is working as expected. It is fine because cache invalidation is supposed to bring everything up to date, which almost always works, but not this time. In this case, it ran into a rare transient error on the cache host, which triggered error handling code, which looks like this. It's saying, drop the item in cache if its version is less than specified. But the inconsistent cache item had the latest version, so this code did nothing, leaving the inconsistent data in cache indefinitely. This is the bug. I have to simplify the example quite a bit so it can possibly be explained on the side. The real bug is even more intricate, which involves database replication, etc. The bug only gets triggered when all the aforementioned rare events happen, and happen specifically in this sequence. You see how deeply the bug is buried, hidden behind interleaving operations and transient errors. Many years ago, finding the root cause of such a bug would take maybe a week from someone who is very familiar with the service, if the person is lucky enough to find it at all. I once spent an entire week doing nothing but debugging a cache inconsistency. It's not fun. In this case, Polaris, the monitoring service, identified the anomaly and fired an alarm. With information from consistency tracing, it took the on-call less than 30 minutes to pinpoint the bug. I'm not sure how to measure the engineer suffering we reduced, but this is obviously a much better pleasant experience than sticking or even thinking about sticking a fork in our eyes. So this is how we made our caches more consistent with a generic, systemic, and scalable approach. Cache invalidation might no longer be a hard thing in computer science. Debugging cache inconsistencies can be close to how we debug errors with actionable information. As I said at the beginning of the talk, my goal is to reduce engineer suffering from cache invalidations, so we can spend more time on building awesome things. The same principle and methodology I covered here should be applicable to your cache services with invalidation as well. Our work is not done yet. We want to get the consistency of all our cache services as close to 100% as physically possible. Consistency of disaggregated secondary indices pose an interesting challenge which we're working on. We're also measuring and meaningfully improving cache consistency at read time. Last but not least, we're working on a consistency API for distributed systems. Think about C++ memory order, but for distributed systems. If you are interested in any topics covered in this talk, we would love to get in touch. Thank you.